Welcome to this podcast on electricity, defibrillators, and operating room safety at the University of Kentucky College of Medicine, Department of Anesthesiology. My name is Dr. J. Thomas Murphy, and I'm going to lead you through this combination of topics somewhat related. Titled Electricity, Defibrillators, and Operating Room Safety, I'm going to flip it around and speak about operating room electrical safety and then defibrillators. I must disclose that I have no financial relationships with any corporation and am receiving no compensation for this, and I wish that I understood electricity better than I do. I am not an engineer, and if any of you in the listening audience are physicists or engineers, please accept my apologies. Now, the ABA content outline from January 2014 gives you the topics that you are expected to learn for examination and clinical practice purposes, and from that outline I have reproduced on this slide the topics for this podcast, which you can read and review. The references that I'm using for this podcast are taken from the 7th edition of Clinical Anesthesia by Barish and from a textbook titled Anesthesia Equipment Principles and Applications, 2nd edition, both authored by Dr. Aaron Worth and Dr. Seifert. And new for this podcast, I'm using chapter 109 from Miller's Anesthesia 8th edition. And for the defibrillators, I am using Anesthesia Equipment Principles and Applications, 2nd edition, chapter 19. Most, if not all, of these are readily available to you at the University of Kentucky through the library, electronic e-books, or through Clinical Key. Largely excluded from this podcast is fire safety. I have extracted just a few points from Miller's chapter 109, and if when you go into the operating room on a daily basis, you should be aware of the location of the fire extinguisher, the location of the oxygen shutoff valves to your room. If you are having an electrical fire, don't use water to extinguish it. And more recently, with the resurgence of oxygen-powered fires in the operating room, it's recommended that if you are using blow-by oxygen during a case of sedation, it should not end up providing fuel in the presence of the presence of a source of ignition. Most modern textbooks have key points at the beginning of their chapters now, and I'm going to bring to your attention some of the key points from the 7th edition of Clinical Anesthesia. And the first one is that Ohm's law applies to electricity. It's a basic principle. Voltage equals current times resistance. Second, to have a completed circuit for a closed loop must exist, and a voltage source must drive the current through the impedance. To receive a shock, one must contact electrical circuit at 2 points, and there must be a voltage source that causes the current to flow through an individual, giving you the electrical shock. Fourth key point, in electrical terminology, grounding is applied to two separate concepts: the grounding of electrical power and the grounding of electrical equipment. In the operating room, In order to provide an extra measure of safety from gross electrical shock, MACROSHOCK, the power supplied to most operating rooms is ungrounded. Next point is that the line isolation monitor, called LIM, is a device that continuously monitors the integrity of an isolated power system, which is how electrical power is provided to the electrical outlets in most operating rooms. Alternatively, a ground fault circuit interrupter is a popular device used to prevent individuals from receiving electrical shock in a grounded power system. You see these in your wet locations at home, and you'll see a photograph of a GFCI later in this podcast. An electrically susceptible patient, that is, one who has direct external connection to the heart, such as from a central line, may be at risk from very small currents. This is called microshock. Where ESUs, or electrical surgical units, are concerned, problems can arise, complications in other words, if the electrical surgical return plate is improperly applied to the patient, or if the cord connecting the return plate to the ESU is damaged or broken. So, Ohm's law, E equals IR, where I is the current in amperes, E is the electromotive force, or volts, and R is resistance. The next physical formula in electricity is power is the product of volts and amperes and is measured in watts. And this formula is abbreviated P equals E times I, or as I learned in school, P equals IE, pi. Different kind of pi. From electrical power, we move to electrical work. And work is the product of power in watts over time in seconds, such that 1 joule is a watt second. Joules are how we communicate the amount of energy used for cardioversion and defibrillation of patients. With respect to electrical work and heat, wattage can be used to express the amount of heat produced in any circuit by restating the formulas that I've shown you on the previous slides, ending up with P power is equal to I squared times R. And this kind of knowledge helps explain the amount of energy, amount of heat that's created in various medical cauteries, etc. Electrical work and heat. Wattage can be used to express the amount of heat produced in any circuit. Therefore, increasing current or voltage increases heat. Also, increasing the resistance increases power or heat. To bring an example, an everyday example into play, a 60-watt light bulb draws a current of 1/2 ampere at 120 volts. Half an ampere. It's a very small fraction of the current that the circuit will allow before a circuit breaker will trip. However, as you can see, the effects of 1 second contact of 60 cycle alternating current on an average human requires very little amperage or current to cause damage. I find it particularly interesting to see that the let-go current has been determined, and the let-go current refers to the phenomenon of the hands, fingers going into a spasm and the inability to let go during electrical contact. So what kind of electricity do we use? Well, primarily in our houses and in the operating room we use alternating current, called AC. However, everything that relates to Ohm's law, as discussed so far, is primarily true for direct current. And for alternating current, things are much more complex because of impedance, capacitance, and inductance. Impedance is defined as the sum of forces which oppose electron movement in an alternating current circuit. It consists of resistance in ohms, but also takes capacitance and inductance into account. Capacitance is the ability of a capacitor to store electrical charge. It is constructed by placing an insulator between two conductors. It's kind of like a battery. Capacitors are found in electronic equipment and can deliver an electrical shock. With direct current, a capacitor is charged by a voltage source, but no current flows unless a resistance connects the two plates of the capacitor. With alternating current, the nature of alternating current allows current to flow through a capacitor. Because the effect of capacitance varies inversely with alternating current frequency in hertz, the greater the alternating current frequency, the lower the impedance. ESUs use high frequency currents, for example 0.5 to 2 million hertz, rather than the 60 cycles per second that is existent in the wall plugs. Therefore, impedance to current flow is reduced with ESUs. We'll talk about this a little bit later. So capacitors look like this. They're also known as condensers. You've seen things like this in electrical circuits, I'm quite certain. Capacitance, in the world of electronics and electricity, capacitors are used to smooth electricity and for other, quotes, beneficial purposes in electronics. That's not vague, but anyway, probably all you need to know from an anesthesiology point of view. But strangely enough, stray capacitance can develop when two insulated wires of a power cord are connected to a 120 volt circuit. Try to remember this for a little bit later in the podcast. Electrical shock. Now, to receive an electrical shock, one must contact the electrical circuit at 2 points, and there must be a voltage source that causes the current to flow through an individual. This cartoon is a depiction of an individual receiving a shock by standing on the ground and coming in contact with a voltage source and current flowing through the person, and as the legend says, the severity of the shock depends on the individual's skin resistance. Same table as shown a few slides back, just showing you that it doesn't take very much current to cause serious complications of macroshock or microshock, which requires much less current to, for example, cause ventricular fibrillation. Same kind of information presented in a different table from Miller's textbook, and showing you that 1 milliamp for 1 second is a threshold of perception. Sometimes I have felt a tingle, electrical tingle in the operating room over the years, not so much lately, but it's a bit of a worrisome situation in an operating room when you feel electrical leakage. For the purposes of this discussion of electrical shocks, I want to reiterate that macroshock refers to large amounts of current, although not large in terms of the capacity of the circuit, just large relative to the very small amounts that may be occurring through saline-filled catheters, such as a central venous catheter or pulmonary artery catheter. The presence of these catheters in the heart has caused ventricular fibrillation in susceptible individuals in the past, and is a very real and risky situation, and sometimes would not necessarily be the first thing you think of when somebody fibrillates. However, if they have a central line, it is not outside the realm of possibility. So, to recap a little bit some of the previous physical facts, wattage can be used to express the amount of heat that's produced in a circuit. Therefore, increasing current or voltage increases heat in the circuit. Increasing resistance also increases heat through the formula P equals I squared times R. And as mentioned before, a light bulb draws a current of half an ampere if it's a 60-watt bulb. Getting back to the statement about resistance, if a person's skin had a very high resistance, it was not moist or wet, or if there's some sort of electrical insulation, well, the amount of current that would flow into the person at risk would be relatively small, like 1.2 milliamps, which would be barely perceptible. However, if the resistance were lower, a much larger amount of current would flow into this person at risk. Just to quote a statement from one of the references, the longer an individual is in contact with the electrical source, the more dire the consequences, because more energy will be released and more tissue will be damaged. Also, there's a greater chance of ventricular fibrillation from excitation of the heart during the vulnerable period of the electrocardiogram. Just to remind you that all the tables on previous slides were for a 1-second shock. Now, let's move on to grounding. In electrical terminology, grounding is applied to two separate concepts: the grounding of electrical power and the grounding of electrical equipment. As you can see from this slide, in your home, the power is grounded and the equipment may or may not be grounded. In the operating room, the power is not grounded, but the equipment is grounded. Electrical power companies provide power which is grounded, meaning that the earth ground potential is 0, and this is a safety measure for the power company and has been in existence for a long time. The 3 wires that come into your house are called hot, neutral, and ground, and they get attached to the service entrance, and it looks kind of like this in a cartoon diagram sense. This shows a house wiring with power coming from the with wires coming from the power company, and they're labeled black, white, green, and they have a potential difference between these wires of 120 volts. The third wire provides an alternate low resistance pathway through which current can flow to the ground, and this is an attempt to eliminate one condition required to receive an electrical shock, that is, the two contact points to complete a circuit. The ground wire does not usually conduct electricity, but in the event of a short circuit, the majority of the short-circuited or fault current will flow through the ground wire and away from the individual. It is possible that the ground wire will complete the short circuit back to the circuit breaker and trip it, interrupting the power. That is, if the device is grounded and has a 3-prong plug. Now, in the operating room, to provide an extra measure of safety from gross electrical shock or MACROSHOCK, the power is ungrounded. That is accomplished by using an isolation transformer. So there, as the legend mentions, the equipment ground wire is still present in the electrical machine that is being used, but there's no direct connection to ground. Now, line isolation monitors, as shown in this slide, are devices that continuously monitor the integrity of an isolated power system. So, if you remember from the last slide, there was an isolation transformer. Its purpose is to isolate the ground potential. And in this cartoon, an example of a faulty piece of equipment which is plugged into an isolated power system does not present a shock hazard. It converts the isolated power system into a grounded power system, and the fault current can be taken away to ground. The device the line isolation monitor should pick up that there's a fault, and it should provide an alarm. This cartoon brings into relevance the leakage currents or stray impedance that may affect line isolation monitoring, and this area here on the slide shows AC capacitance resulting in leakage current, and it can partially degrade the isolated power system. Now, line isolation monitors apparently have evolved through 3 generations, and the current 3rd generation limb does depend on having both the equipment ground wires intact and its own connection to ground. If the equipment ground wire is faulty, the equipment can operate, but the limb will not alarm. If a second piece of faulty equipment is connected, a shock can occur without the line isolation monitor alarming. So even a line isolation monitor has its limits. Line isolation monitors can give false alarms, and the amount of the current that has been detected is variable, and it can indicate that there's too much electrical equipment has been plugged into the operating room. If the gauge reads over 5 milliamps, for example, it's most likely that a faulty piece of equipment is present. When a line isolation monitor alarms, it's necessary to identify the faulty equipment, which is usually done by unplugging each piece of equipment until the alarm ceases. And using common sense, if the faulty piece of equipment is not of a critical nature, it should be removed from the operating room. Now, as I mentioned before, there is a device called the ground fault circuit interrupter, and this is what it looks like. So these kinds of devices are seen in wet locations such as kitchens and bathrooms. And this device monitors both sides of the current flow in a circuit, and when a condition is detected, then power is interrupted. If this kind of device were connected to a critical piece of equipment in the operating room, then you would have no power to it. So if, for example, this were a heart-lung machine, then that would be an entirely unacceptable condition for the use of a life support system in the operating room. This kind of equipment, this kind of ground fault circuit interrupter is not usually found in operating rooms. However, if it is in an operating room and it is tripped, it is recommended to attempt to reset it once, as a surge in electricity may have been the cause. Now, moving on to more terms, double insulation. Double insulation is a design of electrical equipment that usually has a plastic exterior and could be something like an infusion pump. And the two layers of insulation should prevent current leakage. However, electrical equipment of this design does need to be used with an isolated power system or a ground fault circuit interrupter. Now, there is one point from Miller's 8th edition which I want to bring to your attention, and it is stated that if a power cord for a piece of equipment has a plug with only 2 prongs, that is, no third prong to go into the no grounding prong to go into the third hole of the outlet, the equipment should not be in the operating room. Well, obviously, as you can tell from working in the operating rooms here at UK, this is not an absolute. And doubly insulated infusion pumps are used. However, some very good advice is found in the rest of this key point. And that is simply that you should handle the cord by the plug, and you should not use equipment whose power cords have been damaged, nor should you allow heavy equipment to crush power cords by rolling over them. Now, extension cords. Extension cords are verboten, forbidden, should not be in the operating room. Now, I know that you will see operating rooms that have extension cords in them, and they may be the only solution in some situations. However, if you speak with a clinical engineer, a biomedical engineer, you will find that there is nowhere that is recommended that extension cords be used in an operating room. All equipment should be plugged directly into wall plugs. And this is explained in Miller's 8th edition, and it's summarized that rules from the National Fire Protection Association and the Joint Commission have evolved to generally forbid the use of electrical extension cords in operating rooms and other clinical areas. So using common sense and some organization in your operating room, you should make all efforts to eliminate extension cords in your workspace. Now, let's move on to something called capacitive coupling. This is something that I only became aware of recently, although I'm sure it's been in existence for a long time, and The definition of capacitive coupling is a condition that allows high frequency currents to pass easily and is commonly used by manufacturers in electrical surgical units. And it is the principle for the use of the grounding pad, which is also, or more correctly termed, the dispersive electrode in electrical surgical units and connections to patients. Now, capacitive coupling is described as a subtle and abstract concept, and it can, outside of the electrical surgical unit itself, can account for electrical connections between with the patient apparently being present at high current frequencies, at high frequencies, 100 in the hundreds to thousands of kilocycles per second. Now, I did learn, or found a statement regarding capacitive coupling and the electrosurgical unit in Miller's, describing a burn received by a patient that was caused by the use of an older electrical surgical unit that did not have capacitive coupling, and had it been present, it may have prevented a burn caused by the direct current of a bolt of a battery in a damaged nerve stimulator. So, to summarize, old equipment or malfunctioning equipment combined with some of our monitors, or perhaps the presence of metal in patients' bodies, such as tongue rings and ear rings. Although at first it would seem to be unlikely to cause a burn, apparently capacitive coupling is the explanation for some of these burns that have occurred in patients. Now, I found this article written by Roger C. Odell, who is an engineer or CEO or something for a company. However, you can see that he wrote a special article with respect to monopolar electrosurgical energy in the Journal of Minimally Invasive Gynecology. Now, apparently, there have been a number of complications with electrical burns or such in patients over the years. And while they're not strictly our responsibility, anything that you can do to help reduce a patient's risk is well within your purview of clinical practice. So within this review, I found a few interesting things that I want to share with you, and that is that this concept of capacitive coupling describes the transfer of energy into a patient or through a patient such that a burn or a tissue damage can occur. It's interesting to learn that no defect or fault is required for capacitive coupling to occur. And there are a number of factors which influence the amount of energy and perhaps the part of the patient which is injured. Very complex and somewhat abstract, I will have to agree. So within this review, I did learn a few things again, which I want to share with you regarding the development of isolated ESUs and the design changes which were made to address ground point burns. In other words, the alternate site burns And one of the things that I've learned in reading and preparing this podcast is that um, the injury to the patient at the dispersive electrode is not always um, immediate or immediately noticeable, and these um, uh, burns are picked up later, and some anesthesia references uh, make the point that that we should know that these exist so that we are able to explain to people who are seeking to attribute these to our monitors and equipment, and to educate the people who are trying to attribute this complication to us. And also, I've learned that you know, while there may be systems or equipment that is used to monitor this leakage, it's not universal, and most companies um, put the burden of safety on the perioperative nursing personnel and the surgeon, uh, stating that they should follow the manufacturer's instructions for use very closely. This author, Mr. Odell, is a vendor for a particular kind of monitoring system, so there may be some gain for him in writing this article. Now, let's move on to the National Fire Protection Association standards. Not too much to say here other than there is this foundation, and they do provide recommendations or guidelines for design, and we are all certain that ORs are wet locations. However, some hospital administrators and engineers have lobbied to have operating rooms designated as dry in order to reduce the cost of building and renovating ORs. And as recently as 2011, new ORs in California were found to have been reclassified as dry locations without the knowledge of the anesthesia department. And the electrical service panel was locked for some reason or other. So it's important for you to realize that we may have assassins out there trying to save money and um, set us up for unsafe clinical practice with respect to electrical power. Let's see now. So, so we may be all right now. However, it is recommended that anesthesiologists remind administrators and engineers that operating rooms are wet locations, and that we should recommend the installation of isolated power systems in operating rooms in order to minimize the risk of electrocution. So, this podcast moves forward to defibrillators. Now, my main reference is Chapter 19, authored by Ross Zoll. The name should tell you that it is an expert in defibrillator design and production. The short history of defibrillators is that through the 40s, 50s, 60s, and 70s, they have been developed and have transitioned from being external devices to now being internal devices. Our ABA content outline gives you a few keywords to hone in on, and I'll attempt to address some of this, although it's pretty dry stuff, and I think that you know, your own individual reading is going to be key. I'm going to bring up a few key points here. And defibrillation is a treatment that stops the dysrhythmia, ventricular fibrillation, so that normal cardiac rhythm can resume. A defibrillator is a complex device that uses a capacitor to store electrical energy and to release it in a prescribed way. Both alternating current and direct current are involved. The shock is direct current. The advances in waveforms are such that now a rectilinear biphasic waveform has been created, and it reduces the peak current administered while delivering an effective dose. And if you remember that current is equal to injury or damage, however, this is a controlled amount of electrical energy delivered in the form of current. Now, the resistance to current flow decreases after a dose of defibrillation. So, after a shock, repeating the same dose may be as effective as increasing the dose of current. And this is probably something you've learned through reading and talking amongst yourselves, that the second defibrillation, if administered shortly after the first, is more likely to be effective. So, what is fibrillation, and how does defibrillation work, and is defibrillation without complications? So, first, just a cartoon of a typical defibrillator circuit. It's a capacitor. So we've been talking about capacitors. It's something electronic, and it stores energy and it's released. A few more definitions. Fibrillation is a random and chaotic re-entrant arrhythmia. And the myocardium is in a unique, unreproducible state, which is part activated, part refractory, and part relative refractory, and part perhaps resisting. The basic principle of defibrillation is to interrupt random and chaotic electrical activity in the heart by using a large stimulus that excites a large and sufficient fraction of the muscle mass at one time. In your studies, you'll review that there are many factors which influence the success of defibrillation, and the duration of ventricular fibrillation, the severity of hypoxemia, and acidosis all have an effect on the success. Of the controllable factors that influence defibrillation, these appear to be impedance and current flow. Controllable insofar as this is something that is within your control, outside of the primary cause of the fibrillation. Now, current flow in the myocardium depends almost entirely on delivered current and, quotes, geometric factors. And it's stated that there are wide variations in patient impedance affecting the delivered dose. So while we set the defibrillator at a certain number, the actual delivered dose could be quite different between patients. It is stated that the new rectilinear biphasic waveform, which is what we have in our Zoll defibrillators, provides a more effective shape for energy delivery, and this is what a rectilinear biphasic waveform looks like. And it is just simply more efficient. So, as I mentioned, the first shock reduces impedance, so a second shock may be more effective. Now, since patient impedance varies by more than twofold, factors such as patient weight and other factors such as the interface, whether or not, how much gel is used, or whether or not reusable, or whether or not single-use pads are used, and the paddle pressure have less effect on the success of defibrillation than patient impedance. A fact that I came up with in my search for information was that the presence of myocardial patch electrodes significantly interferes with defibrillation. What are myocardial patch electrodes? Well, at one time, implantable defibrillators had myocardial patch electrodes sewn onto the outside of the ventricle. And in this day and age, they're largely implantable defibrillator electrodes are transvenous. Now, here's a famous case report from our institution describing a multiple failed external defibrillation attempts due to the iatrogenic pneumothorax created for one lung ventilation. So air is a very effective insulator, and this was the explanation for the difficulty in treatment of ventricular defibrillation in this particular case. These graphs show a dose-response curve showing that the relationship between peak current and clinical success. This is a fairly old slide, but does show you the dose-response relationship. So is defibrillation without complications? Well, nothing's without complications. So just extracting this paragraph sums up the fact that too much current can cause damage to the myocardium, which may not be thermal in nature. Cell membranes and contractile structure could be damaged, leading to depressed function, necrosis. Overdose of current may result in failure to defibrillate. However, there is clearly a therapeutic window for effective defibrillation. It's not as quantitative as you would like, but this is the best one can do with the feedback that one is getting from an emergency defibrillation situation. In the field of pediatric resuscitation, I'll just provide you with the recommended dose of current or energy for defibrillation, and it's what is recommended is a dose of 2 joules per kilogram for the first attempt and 4 joules per kilogram for subsequent attempts. More about defibrillators, it's been shown that there's a wide range of body weights. The dose does vary with weight. Going back to impedance, the interface material can add resistance to the circuit, and paddle pressure, increased paddle pressure usually reduces impedance by 5 to 10%. As compared to the self-adherent patches without pressure. So we put these defibrillator patches on, and it probably is not obvious that they may not be as effective as external paddles. However, they are very convenient, and they can be prepped into the surgical field, and they are definitely helpful in defibrillating patients who do not have access to the heart, but through a reduced sternotomy, or who are undergoing cardiac surgery. So this is just an advertisement from Zoll, and it's dated insofar as it's comparing 100-watt incandescent bulbs to compact fluorescents. In this day and age, LED bulbs are now becoming much more energy efficient, and who knows how long CFLs will even be on the market now. So I thank you for your attention, and apologize for the long podcast. I hope that you are able to use the information in this podcast to go through the quiz questions, which will be part of the block. The quiz questions, I'll take no credit for their creation. I lifted them verbatim from authoritative quiz question books, so therefore I'm quite confident that they are accurate, and in my submission of the quiz questions there is an explanation for each quiz question. I'm not quite sure how that will be provided to you, or how the podcast quiz question interface will be created, but if you have any difficulty accessing the quiz question answers and explanations, just let me know, and I'll make sure that that this information is made available to you. So in conclusion, I thank you for your attention, and if you have any feedback on these podcasts, I'll be happy to take them by email. Thank you.